SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and in today's class we shall solve two numerical problems on engine performance. In the last few classes we have discussed about the thermal performance of both Otto and diesel cycles. As such, through the discussion of this particular topic, that is the thermal performance analysis, we could establish the mathematical form of thermal efficiency of both SI and CI engines. So, now we shall solve two problems on engine performance, and we will see that from the given data, if we need to, of course, from the given data, those are required to design several components of internal combustion engines. How can we perform, how can we estimate the efficiency and several other several other performance measuring parameters. So, the first problem is given here. Let me read out the statement of this problem. A 4-stroke cycle CI engine has a brake thermal efficiency of 32%. So, now though we are yet to discuss about several efficiencies of internal combustion engine, but we could discuss about the brake thermal efficiency when we had discussed about several parameters like brake horsepower, indicated horsepower, brake power, indicated power, etc. So, brake thermal efficiency, you know that in the last 2-3 classes we could establish the thermal efficiency of both Otto and diesel cycles. So, when it is brake thermal efficiency, definitely it is the efficiency which is calculated based on the brake power. So, now if we write, so this is the solution. So, brake thermal efficiency, eta thermal brake, we know the mathematical form of this efficiency, that is nothing but the brake power W dot V as the ratio of brake power, that is the power available at the shaft, to the amount of energy that is supplied to get this amount of power. So, this is m dot F into calorific value of the fuel. So, this is the expression. So, this is mass flow rate of fuel and this is calorific value of fuel. So, now let me read out the rest of the statement of this problem, and the lower heat value of the fuel is 41,200 kilojoule per kg. So, QCV is given 40. So, QCV equal to 41,200 kilojoule per kg, and what we need to calculate? We need to calculate the brake specific fuel consumption and brake mean effective pressure of the engine if the volumetric efficiency is 76%. Inlet density of charge is 1.05 kg per meter cube and fuel air ratio is 0.04. So, now it is though a written charge, but for the CI engine normally we need to supply air through the intake manifold into the engine cylinder, but we could define charge as the mixture of air and fuel. So, it is charge means basically it is the air for the CI engine. Now, one new term that we are getting today is the volumetric efficiency, though I could not discuss about this particular efficiency, but for the time being to solve this problem I can tell you the mathematical expression of this efficiency and what this efficiency is all about. Now, volumetric efficiency is given 76%. So, I am writing eta volumetric equal to 76%, and inlet density of charge is given, that is I can write rho inlet, that is 1.05 is given kg per meter cube, and fuel air ratio is 0.04. So, fuel air ratio, that is m dot f by m dot a equal to 0.04. It is also mf by mf. So, this is given. Now, from this particular this brake thermal efficiency is given 32%, right. So, this quantity is 32%. So, from there, so what we can calculate, that we know QCV, we know brake thermal efficiency, and mass flow rate of fuel we do not know. We also do not know about the rate of work done that is available at the shaft, that is the brake power. So, we can easily calculate what would be the value of m dot f by w dot. So, m dot f by w dot b equal to 1 upon QCV into eta thermal brake. So, this is equation number 1, because we know QCV and this quantity. So, if we go to the next slide, because you can see the first quantity that we need to calculate is the brake specific fuel consumption. So, that is BSFC. We have discussed about specific fuel consumption, and we can also write the specific fuel consumption by adding prefix to it I or B. If it is I, then indicated specific fuel consumption. If it is B, then it is brake specific fuel consumption. So, now let us now move to the next slide, and brake specific fuel consumption, that is BSFC. So, this BSFC is nothing but, if we can recall the formula, then we can write that the mass flow rate of fuel, that is the amount of fuel needed to be supplied to the engine to get the brake power. So, this is m dot f by w dot b. So, if you would like to get unit brake power, the amount of mass flow rate we need to supply to the engine, that is the brake specific fuel consumption, BSFC. Okay. So, what would be BSFC? already we have written this quantity. So, this is nothing but QCV into eta thermal break. So, this we can write from the previous slide, because we had written that this quantity can be written in terms of calorific value of the fuel and break thermal efficiency, and if we calculate it, we will be getting this is 7.58 into 10 power minus 5 kg per second kilowatt. You can see the unit, because mass flow rate of fuel, that is kg per second, divided by break work, that is kilowatt. Now, what we can do, you know that it is quite convenient to write this unit like kg per bhp hour. So, basically that is the common unit of this quantity. So, what we can do, we know that 1 brake horsepower equal to 0.746 kilowatt. If that is the case, so we can replace this kilowatt in terms of brake horsepower. So, I can write this BFC will be equal to 7.58 into 10 power minus 5 into 0.746, that is the it should be right bhp, and then multiplied by 3600. So, we can convert the unit second to hour, it would be kg per bhp hour, and if we calculate it, you will be getting this is 0.2 kg per bhp. Normally it is written bhp. So, this is I can write it. So, this is bhp, this is bhp, right. So, this is the brake specific fuel consumption. So, the answer to the first part of this question is brake specific fuel consumption BSFC, and that we have already calculated, that is 0.2 kg per brake horsepower hour. Okay. Next is what is brake mean effective pressure. Okay. So, brake mean effective pressure is, let me write it, what is brake mean effective pressure. Brake mean effective pressure, that is BMEP. So, this BMEP is, if we try to recall, W dot B divided by this displacement volume into N divided by small n. This is the expression. Now, this small n is number of revolution per cycle. So, it is 4 stroke engine. If we go back to the previous slide, it is 4 stroke cycle engine. That means, small n equal to 2, small n equal to 2. So, I can write it, that would be twice into W dot B divided by Vd, that is displacement volume, into N. Okay. Now, we have no clue about the displacement volume from the data set given, right, but importantly the expression, rather the numerical value of volumetric efficiency is given. let me tell you once again, we did not discuss about the mathematical expression and the definition of volumetric efficiency, but we need to use this particular term today. So, I am writing here the volumetric efficiency eta volume. So, this is that is written, you know, that is twice m dot f plus m dot a, right, rho I into V d into n. As such, I will be writing like this. I will not write like this, I will be writing n by small n. So, you can understand that we are supplying the amount of air during the intake stroke, of course, per cycle, right. So, there are 2 revolution per cycle. So, definitely, but so per cycle we are supplying, this is the amount of air that is drawn into the cylinder. Now, issue is, but we need to supply m dot f plus m dot a, that is the kind of total, though it is written charge. So, basically, so the volumetric efficiency, so I will be discussing this particular term, physical significance as well as from where we are getting this definition, but for the time being today we assume this is the mathematical expression. So, now you know that from this expression small, so I can write it. So, that would be twice into m dot f plus m dot a divided by rho I into V d, right. Now, if we need to calculate break mean effective pressure, we need to know about this V d. As such, we can get this V d from this volumetric efficiency. So, this is volumetric efficiency, and it is given, volumetric efficiency is given, if we go back to the previous slide, 76%, it is given 76%. So, I am writing here, this is 0.76. So, from you remember that we need to calculate this quantity, break mean effective pressure. So, we know that this m dot f by m dot a equal to 0.04, right. So, I can write m dot f in this expression in terms of m dot a. So, what I can write is, if we go to the next slide, that 0.76, that is the volumetric efficiency, that is nothing but 2 into 1 by 0.04, that is 25 plus 1 into m dot a. I can take out m dot a outside and divide by 1.05, that is rho I into V d into n. So, from there we can calculate V d into n, that is equal to, right. So, 2 into 26 m dot a divided by 1.05 into 0.76, and it is coming as 65.1629 m dot f. So, we could write V d into n in terms of this m dot f. Now, if we go back there, so basically we need V d into n to get break mean effective pressure. So, we could calculate V d into n, and we also can get W b from the break thermal efficiency, right. So, we also can get, so basically you know that what is Bs Fc, that is m dot f by W dot b. So, from there we can get W dot b equal to m dot f divided by 7.58 into 10 power minus 5 kg per kilowatt second. So, now, so we have W dot b, which is again in terms of m dot f, and we also have Vd into n. So, W dot B we could write in terms of m dot f, we also could write Vd into n in terms of m dot f. So, m dot f is appearing both in numerator as well as denominator. So, that we can cancel this m dot f, and finally, we can write the break mean effective pressure, right, that is twice into m dot f divided by 7.58 into 10 power minus Vd into n 60 into Vd into n. So, this is the W dot B. So, this is the W dot B, right, and Vd into n is 65.1629 m dot f. So, this is Vd into n and this total is W dot B. So, if we calculate, you can see that m dot f is appearing both in numerator as well as in denominator. So, we can get it BMEP equal to 0.42 megapascal. So, if we go back to the problem statement again, so from the quantities given we could calculate the break specific fuel consumption as well as the break mean effective pressure, but most important part of this particular problem is we can see a new term, that is volumetric efficiency. Though I have used the mathematical expression of this particular term, but we shall discuss about this particular efficiency again in one of the next classes. Okay. So, this is all about the first problem, and finally, we can solve another one problem. So, if we go to the next one, so if we go to the next one, okay. So, this is the problem. So, this is the second problem. The problem is little lengthy, but we can first read the problem statement. In a constant speed CI engine operating on a 4-stroke cycle and fitted with a rope brake, the following observations are recorded. Brake wheel diameter 60 centimeter, band thickness 5 millimeter, speed 450 rpm, load on band is 21 kgf, spring balance reading is 3 kg force, area of indicator diagram is 4.15 centimeter square, length of the indicator card is 6.25 centimeter, spring scale is 21 kgf per centimeter square per centimeter, bore diameter is 10 centimeter, stroke is 50 centimeter, specific fuel consumption is given 0.22 kg per bhp hour. You can see that in the previous problem we could calculate the brake specific fuel consumption, that was of course BSFC, but here it is given specific fuel consumption, that is 0.22 kg per brake horsepower. So, basically it is again BSFC per hour. Heating value of the fuel is 10,000 kilocalorie per kg. Determine brake horsepower, indicated horsepower and mechanical, brake thermal and indicated thermal efficiencies. So, you know that though we are yet to discuss about several efficiencies, you can understand from the problem we are going to solve today. Already we have discussed about volumetric efficiency. In the previous class we have discussed about the mechanical efficiency, and we are also going to see there are two other efficiencies like brake thermal and indicator thermal efficiencies. So, basically at the cost of the input energy, brake work and indicated work, these two works are not equal. So, if we calculate, if we consider the indicated work to calculate the efficiency, then definitely it would be indicated thermal efficiency. On the other hand, if we consider the brake work, that is the work available at the shaft, and then it would be the brake thermal efficiency. Okay. So, now and mechanical efficiency, you have seen that as I said you that the work which is available at the shaft is not equal to the indicated power, because there are several losses to overcome the friction between the mating components. So that is why mechanical efficiency is coming into the picture. I am telling once again, we shall be discussing about all these efficiencies in one of the next classes. So, we can solve this problem. You know that there is a test in thermal engineering lab, and the test is done on internal combustion engine to calculate all these parameters. And normally in lab scale, what is done, you know, that this rope brake is used to provide load to the engine, because if we do not provide load to the engine, then we cannot calculate what would be the, you know, because the load is given and load is measured. So, at the cost of that load, what is the what would be the you know, several efficiencies that we can calculate. Okay. So, here it is rope brake. Let me so basically, you know, I am drawing one schematic. So, this is basically the brake diameter. So, this is diameter of the wheel, D wheel, and if we use another color, say this is, so this is the band. So, this is the brake wheel diameter, and there will be one band. So, you know, this is the band that is shown by this green color. It has certain thickness, and this band is, this is fixed. So, this band, you know, that so this is the band I am writing here. So, this is the band, and dW is the, so dW is the wheel diameter. Okay. What is done, you know, that this brake, this wheel is rotating, because when engine is rotating. Now, if we try to wrap one band over the periphery of this particular wheel, and if we try to that is spring loaded, you can see, and if we try to just tight the band, then perhaps the spring you know balance will give one reading, right. So, from there we can say, we can measure the load being applied you know, so that by an external this arrangement, rope brake arrangement. So, the load which is applied to the engine by this external arrangement. So, from there, from that particular load, we can calculate several other, you know, performance measuring parameter. So, now question is, first we can calculate brake power, because this arrangement is to measure the brake power. So, what is the amount of work available at the shaft? So, basically say engine is, you know, as I said you that the engine, if you try to recall the schematic depiction, engine is having reciprocating movement between two centers, BDC and TDC. Now, that reciprocating motion is converted to the rotary one using the crank and connecting rod mechanism. So, now we are having the wheel is rotating, and from there I mean that wheel is connected to a shaft. So, if we can measure the work or power available at the shaft by using this particular arrangement, that would be the brake power. So, we can write brake power. So, this brake power is, you know, I am writing W minus S into 2 pi into D plus dW, sorry I am writing, I am using small d. So, this brake power equal to W minus S into 2 pi into dw plus that is band thickness, that is T by 2 into n, right, divided by 60. So, if we calculate it, we can, so T is the band thickness, right, and dw is the wheel diameter, brake wheel diameter, and this S is the spring balance reading. So, this S is the spring balance reading, right. If we calculate it, we know all these quantities. N is given RPM, N equal to RPM 450 RPM. Okay. So, we are dividing by 60 to get it the kg force into meter per second, and if we calculate it, and W is the load on the band, W is load on the band, that is given 21 kg force. So, this is load on band. So, W is load on the band, right, and then we can get it, this is coming as 256.58 kg force into meter per second. So, this is the brake power, and we can get it brake horsepower, that we can get it brake horsepower, right. I am writing over here 1 horsepower equal to 75 kg force meter per second. So, we can convert it, right. So, this amount of, right, that is given. So, brake horsepower, that is bhp. So, from there we can calculate bhp. So, that is brake horsepower, that would be equal 3.42 horsepower, right. So, 1 horsepower equal to 75 kg force per meter per second. So, if I divide by 75, then we will be getting 3.42. So, this is the first part of the problem. If we go to the next slide, it is given that indicated diagram, area of the indicated diagram, because this is what is done in testing. So, if we know the area of the indicated diagram, and length of the indicator card is also given 6.25 centimeter. So, using this data, so area of indicator diagram AI equal to 4.15 centimeter square, and length of the indicator card, right, Li equal to 6.25 centimeter, right. Spring scale also it is given, spring scale equal to, that is alpha, that is 11 kg force per centimeter square per centimeter. So, we have all these information I am writing. Okay. Then what is indicated mean effective power IMEP. So, indicated mean effective pressure. I told you that the pressure inside the cylinder is continuously changing, right, but we could obtain the integral expression of that, the work done. So, this indicated mean effective pressure is this area of the indicated diagram into this alpha, that is spring scale, divided by Li. So, if we do this, we will be getting 7.304 kgA per centimeter square. Okay. What is given, that bore diameter is given 10 centimeter, stroke length is given 15 centimeter, right. So, what is area of the bore? That is pi by 4 into 10 centimeter square, that is 75 into 53 centimeter square. So, bore diameter dB, bore diameter is dB. So, this is pi by 4 into dB square. So, we are getting this. Now, so what is the, if we know the stroke length, then we can calculate the volume, right. So, this is Vs, that pi into pi by 4 dB square into stroke length Ls. So, if we go back here, so this is writing Ls, stroke length 15 centimeter. So, then we can write this is coming as 1178.09 cc cubic centimeter, right. BSFC, brake specific fuel consumption, that is already given 0.22 kg per bhp. If we go back to the problem statement, that is 0.22 kg per bhp hour, though it is specific fuel consumption, but from the unit itself you can understand that is brake, because it is brake horsepower. So, that is hour, right. So, we can calculate indicated work, that is Wi per cycle, that is IMEP into Vs, stroke volume. So, this is the stroke volume. In one stroke the volume displaced by the so this is not Wi, this is per cycle we can write. So, we can write that equal to if we write it here, indicated mean effective pressure we have already calculated, and we will be getting 86.04 kg force meter per cycle. Okay. So, we could write it. Now, what about indicated power? Then if we go to the next slide, indicated power IP, that is Wi into n divided by 60 into small n, and if we calculate it we will be getting 322.67 watt, and so this is indicated power. And I can write indicated horsepower. So, this is indicated horsepower, that would be equal to, it would be less than this. So, 4.302 horsepower. Now, from there we can calculate what would be mechanical efficiency, that is nothing but brake horsepower divided by indicated horsepower, right, and if we get it, that would be 0.7952, 79.52%, because we have calculated indicated horsepower 4.302 horsepower, and brake horsepower, if we go back to the previous slide, we had written that the brake horsepower is 3.42 HP horsepower. So, the ratio of BHP by IHP, definitely indicated horsepower is higher, and the certain amount of indicated power will be used to overcome the frictional loss. So, now if we go to calculate the, what we have to calculate, next problem statement is brake horsepower we have calculated indicated horsepower, we have calculated mechanical efficiency. So, we need to calculate brake thermal and indicated thermal efficiencies. Okay. So, if we go to this slide, then you know already we have calculated brake specific fuel consumption. So, eta thermal brake, that is brake horsepower divided by BSFC into QCV. See, this is the W dot B divided by BSFC into QCV. In fact, we have used the same expression when we have solved the first problem, and if we calculate it, we all know. So, we know the BSFC that we have written over here, we know QCV because calorific value of fuel is given 10,000 kilocalorie per kg. So, QCV, that is 10,000 kilocalorie per kg, and if we calculate, then we will be getting 0.287. So, this is the brake thermal efficiency, and indicated thermal efficiency, thermal I, that is nothing but eta thermal brake divided by eta mechanical, because this mechanical efficiency. So, actually sorry, I have written over here. So, mechanical efficiency already you have calculated, that is 0.7952, right. Now, this mechanical efficiency eta mechanical can be written eta thermal brake divided by eta thermal indicated. So, naturally knowing these two quantities, that is mechanical efficiency and brake thermal efficiency, we can calculate what would be indicated thermal efficiency, and that is what I have written over here, that is indicated thermal efficiency is equal to eta thermal brake by eta mechanical, and it is coming 0.3614, and it is coming as 0.3614. So, 36.4%. Definitely, because you can understand that indicated thermal efficiency is higher than the brake thermal efficiency, and that should be. So, we have calculated as per our expectation. So, basically what we have understood that the indicated power is higher than brake horsepower, naturally indicated efficiency will be higher than the brake efficiency, thermal efficiency. So, to summarize, we have solved two problems on engine performance and we have seen that from the given set of data, if we need to calculate several performance measuring indices, then how can we calculate? We have solved considering two different problems. With this I stop here today, and we shall continue our discussion in the next class. Thank you.